even if it's symmetric about the y-axis. Now the function we studied last year could be even. Alright, so last year we studied the parabola, right? And if we looked at the parent graph for this quadratic function, it looks like this. Whoop. Oh, that's terrible. Anyway, it's symmetric about the y-axis, if you can draw. There we go. So what that means is if I fold it right down the y-axis, it would fold on top of itself. Right? So this parent graph for the quadratic has even symmetry. It would be an even function. But what happens if I took this function and moved it, shifted it left to? If I fold it down the y-axis, does it fold on top of itself now? No. No. So even though it's an even degree function, it doesn't have to have even symmetry. Symmetry is symmetric across the y-axis. Make sense? Okay. Now, a function is considered odd if it has rotational symmetry. And that rotational symmetry occurs about the origin. Okay, so an example of this would be one of our cubic functions, especially one that has that inflection point right there at the origin. So what that means is, if I thought about this as a spinner, and this is where my pin is, if I flick it and I spin it round and round and round and round, and it can go 180 degrees and fall right back on top of itself. So if I can do a rotation of 180 degrees about the origin, and the graph falls right back on top of itself, it has odd symmetry. Okay, so even is symmetric about the y-axis, and odd has that rotational symmetry about the origin. Okay, so let's look at these. Now, if I fold this one over the y-axis, does it fold on top of itself? No. If I thought about this being my little anchor for a spinner, and I spun it around 180 degrees, does it fall on top of itself? Yes. This one has odd symmetry. It is an odd degree function, but it also has odd symmetry. And last period someone asked, isn't there an algebraic way to look at this? Well, do you guys remember when you studied rotations about the origin? And we would say that any point xy gets mapped to the opposites, negative x, negative y. Okay, so like this point right here would be about 0.5, 1.5. Well, isn't this negative 0.5, negative 1.5? So that's a rotation of 180 degrees. All right, B. If I fold it down the y-axis, is it symmetric?
Yes.
Yes. So this one has even symmetry. You would call this an even function because it has even symmetry. All right. Now, as math teachers, we kind of have to work hard to make this happen because not all functions, even functions that have even degree will have even symmetry. If I shift this the slightest bit one way or the other, it no longer has even symmetry. Just like this one. Do you guys see that this axis of symmetry is right here.
Yeah.
Is it exactly on the y-axis? No.
That's cool.
So it doesn't have even. And it also doesn't have rotational. So this is neither even nor odd. And honestly, most functions are neither even or odd. They neither have even symmetry nor odd symmetry.
It's amazing how that works.
I agree. Alright, so that's how we do it graphically. But there's actually two ways. The other way is algebraically. So if I gave you a test and part of it was graphing calculator and the other part was no graphing calculator, the algebraic questions would be on the no calculator part. So how would we do algebraically? With an even function, if we plug in the opposite of x and we get out the original function, it is considered even. So when we plug in a negative x, all of our terms remain the same. But with an odd symmetry, if we plug in the opposite of x, we get the opposite of the original function, which means that all of our terms become the opposite. Okay, so let's look at some algebraic problems. We're going to do these. Was that not long enough?
I get like 10
Sure,
seconds.
Beth.
Yeah, you're right. It is, you have 13 seconds if you want. Alright, I'm fine. Just get it.
No.
They're putting so much pressure on that.
No pressure, buddy. No pressure.
I'm good.
You okay?
Period.
Okay. Alright. So, let's look at 3. And since we have 3, we're probably going to have an even, odd, and a neither, aren't we? Probably.
Chances.
Alright. So let's look at the first one, A. If we plug in the opposite of x, how do we do it? Every place there's an x, put a big parenthesis.
Should we calculate this? No.
We don't need to calculate this. Because all we're plugging in is negative x. So really all we're dealing with is, does the sign change or does it not? So a negative raised to an odd power becomes negative. Or stays negative. So this turns into this. A negative to an odd power becomes negative x cubed. And what happens when I multiply negative 5 times negative x cubed? Positive 5x cubed. And here, negative x times 4 is negative 4x. So this is where we compare our original function to what we got when we plugged in the opposite of x. Do you see the first term changes to the opposite? The second term changes to the opposite, and the third term changes to the opposite. All the terms change signs. So this one has odd symmetry. This one is odd. That's all you gotta do. Okay, let's look at B. So let's evaluate this function when we plug in a negative x. That's exactly what's about to happen. So this time we're raising these negative x's to even powers, so they become positive. So this becomes positive x to the 4th. Positive x squared times negative 3. Alright, so now we gotta compare. How does that original function compare to when I plugged in negative x? Same, same, same. All 3 terms are the same. So that is an even. This one has even symmetry. So if they all change to the opposite, they're odd. If they all stay the same, they're even. But if we have a mixture, some change, some don't, then it's neither. And that's what's going to happen on the last one, because look at this. That's going to be raised to an even power, so it's going to stay the same. But this one, when I plug in negative x, will switch to the opposite. Some will stay the same, and some will change. So once I notice that, I'm really kind of done. But this gives us positive 4x to the fourth. This becomes positive 3x cubed. This stays negative 2x squared. And this is positive x. So this one stayed the same. This one changed. Same. Oh, wait, hold on. That's negative x. So stayed, opposite, neither. It is neither even nor odd in terms of symmetry of the function. Questions? Alright, so that's really our only new part. Because the second part is talking about end behavior, and we are good with end behavior. We know rise, rise, fall, 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 rise, fall. Okay. Now, when we look at end behavior, we're looking at two things, the leading coefficient and the degree of the polynomial. So if the degree of the polynomial is even, then the ends move in the same direction. So they're either both rising or they're both falling. Versus if the degree of the function is odd, then the ends are moving in opposite directions. They move in opposite directions?
Ends move in same direction and then opposite direction for the bottom.
Okay, fair enough. Alright, so if it's even, it's going to rise, rise. Even and positive, rise, rise. So we would write as x approaches positive or negative infinity, y approaches positive infinity. But if it's even and negative, it's going to fall, fall. So as x approaches positive or negative infinity, y approaches negative infinity.
Wow, that's a neat trick.
Alright, versus odd. If it's an odd, if the degree of the function is odd and the leading coefficient is positive, it falls to the left and rises to the right. So we have to split it up here because it does different things. So as x approaches negative infinity, y approaches negative infinity. And as x approaches positive infinity, so does y. Which is the opposite here. If the degree of the function is odd and it has a negative leading coefficient, it rises and falls. So as x approaches negative infinity, y approaches positive infinity. And as x approaches positive infinity, y approaches negative infinity. Okay, so two ways we're going to look at it. If they give us a graph,
You
yes,
back.
sure.
Waiting on you soon.
Take your time, Tim.
trying to, learn.
One thing about school is everybody gets to learn Hayes.
Well, you're hindering the process for everybody else.
No child left behind.
Actually,
I
we
don't
got
call
rid
you
of
a
that.
child. You've had
Really?
Did
facial
you know
hair
that?
since 6th
So,
grade.
like, you could
No
just leave me
child left behind is no longer.
What is that?
It was.
See
Is
you
it
in
a law?
Saturday school, punk. Sorry.
Whoa. Hayes is just
It,
not
it
much.
was
Still mad you
instituted
snitched
during
on
the
me.
Bush administration, and it was supposed to
Not leave any children
not
behind.
leave any children behind. But the problem is, some children are just so stubborn and they dig in their heels, and I always felt like we should leave some of them behind. But
Such as?
The ones
Such
that use
as?
their phones in class.
yeah.
Oh.
The ones that feed Sam.
But and I'm old school, so I think you learn best from failure. And I think we've taken away a lot of the opportunities to fail in a safe environment. And so when you guys do fail, you don't know how to deal with it
It'll be in
because we haven't let you deal with it. And so I think that's bad too.
I'm learning how to deal with it after the grade these tests.
You will. Yeah, that's okay. We all fail. We fail a lot. So, alright. It's gotta be odd because they're going different directions. The ends are going different directions. When they go different directions, it has to be odd. And it's rising to the left and falling to the right, so it's gonna have a negative leading coefficient. This one's going in the same direction. So the degree of the function would have to be what? Even. And because they're both going down, a negative leading coefficient. These are going opposite, so the degree must be odd. But it's falling to the left and rising to the right, so that's a positive leading coefficient. So those things we already know just by looking at the graph. We also know this one has 2 real roots and 2 imaginary. Non-real, that's right. Okay, now, how would we describe the end behavior here? Now we have already looked at functions like this, guys, but most of ours were in factored form. And when they were in factored form like this, x minus 1 times x plus 2 squared, we would add up the exponents and we would say, ooh, this one has a degree of 3. But these are not in factored form. These are in standard form. If we started in factored form, they've expanded it out and combined like terms. So when they're in standard form, you just take the term that has the largest degree. And that's all you're looking at, just the term. So do you see the difference? No multiplying, just pick the biggest. Multiplying, add them up. So the degree of this function is 3. So it is odd, which tells us the ends are going opposite ways. And the leading coefficient is positive. So as x approaches negative infinity, y is going to approach negative infinity. And as x approaches positive infinity, so does y. Because when it's positive and odd, this is our end behavior. Okay? This one is negative and odd. So it's going to swap. As x approaches negative infinity, y approaches positive infinity. As x approaches positive infinity, y approaches negative infinity. And this one's negative and even. So both ends are doing the same thing, so I'm going to cheat and write it in one line. As x approaches positive or negative infinity, what's y going to approach on this one? negative infinity. Alright, so your homework is this part, and we went ahead and printed the graphs for you. So that was that third sheet you guys picked up. Now, at the top of the third sheet, it says Advanced Algebra. That was the name of the class last year. Your book also says Advanced Algebra, but it's the right content. The state changed the name of this course this summer from Advanced Algebra to Algebra 2, but it's the same content. It's a fun game our state likes to play.
Just bought all new books, so it's got everything.
So, we're not buying any new books.
We could move the year
Alright,
slide.
speaking of the books, you guys have online access to the books. So you don't have to tote the book around. You can take it and stick it in your locker and go get it back out in May. You can take it home, hide it under your bed, and have to look for it in May. You can't leave it here.
Huh? What if
Go put it in your locker. I'll tell you your combination in May and you can get it back out.
I don't have a locker.
I don't remember where my locker is.
I need a locker.
We got problems.